Brilliant. So what we'll cover is we'll do some stuff around definition because we know that some people say machine learning, some people say AI. There's a little bit of contention about which is which, and some people prefer to use the words in different ways. We'll talk about how machines learn. So we'll go into detail about how predictive machine learning is built, and then how generative AIs are built, and then why the way it's built is important. We'll talk a little bit about how these breakthroughs happen in big tech companies, and why that's important. We'll talk about our strategy for innovating in this space because we don't have the resources that tech companies have. We don't have billions of pounds at our disposal to do these things. And then we'll very briefly touch on low carbon AI. If you attended our last talk, you would have seen the part that says that training ChatGPT was the same as flying from New York to San Francisco more than 1,000 times. We've got strategies for mitigating the carbon costs of AI, and that I think is an important part of our offer. The goals for this session, as I say, I don't want to make you all data scientists. We've got enough technical people to actually make this work happen. But what I want to do is give you an appreciation and awareness and reassurance that we can do AI well. Hopefully you're able to know our offer a little bit better, and hopefully you're able to avoid sort of common mistakes that come along with AI projects. So a technical definition or a historical definition of machine learning is that machine learning is the field of study that gives computers the ability to learn without being explicitly programmed. So this chap in the 50s created a very basic AI that can play checkers. And he imagined engaging with systems in ways that don't require explicit programming. I think someone's mic's on. I'm getting a little bit of an echo. It would be helpful if you can mute unless you have a specific question to ask, if that's okay. So there's an engineering definition of machine learning as well, which is that a program can be said to learn from experience E with respect to task T by some performance measure P, if performance on the task by its measure improves with experience. No one wants to remember that. All that's saying really is that as long as you're measuring how good something's doing, as long as it gets better with each iteration, then it would qualify as machine learning. How I like to think about it, and this lines up with the first definition fairly well, is I like to think of it as a new way of programming where the rules are learned rather than specified. So rather than having to, take time analysing the problem and scratching your head and saying, if the temperature is 11 degrees, then do this. You actually get the machine to do the programming for you by constraining it to a particular problem, particular data set, particular algorithm. So there's this big debate about AI versus ML. I got asked recently by a colleague, like a well-meaning colleague, how much of the work do we do is actually artificial intelligence? And I said, well, all of it, technically. But I know that people don't see it that well necessarily. So AI, generally speaking, refers to any system. It doesn't have to be a computer system. It could be a biological system or whatever else. But any system where you're trying to create an intelligence that otherwise wouldn't have existed. And when we say intelligence, we specifically mean a system that's able to adapt to its environment, right? It's able to observe its environment and change its behavior based on that. So there are quite a few things under the umbrella of AI. But the most popular, the most commercially successful, and the one that has the most sort of research being done on it is machine learning. So specifically writing computer programs that can observe data and rewrite their own rules based on the data that's observed. And there's all sorts of subsections of machine learning. There's unsupervised learning, supervised learning, reinforcement learning, deep learning, generative learning, all sorts of other amazing subdisciplines within machine learning. So what I'm saying here is not all AI is ML, all ML is AI, because ML is a subset of AI. However, I appreciate for most people that's not enough. So the way I like to think of it is that AI is a major driver of innovation, right? And the promise of innovation is about either doing the things we do currently but better, or doing entirely new things. So the sort of rule of thumb I tend to apply is if it fits in the better category, doing what we're doing but better, that feels like ML. And then if we're doing something completely new, that was totally impossible before, I'd call it AI. And there's an even simpler version, which is if it's super flashy, feel free to call it AI. People won't be offended if you call it AI if it's super flashy. So we talk about GPT as being AI. We talk about Midjourney as being AI and other such things because it's the state of the art and it's easy to point it and call it AI, whereas strictly speaking, it's machine learning. One thing not to get bogged down on, though, is discussions about big intelligence. So there's this term in the industry called artificial generalized intelligence, and this is when people start talking about, Terminator and AIs that take over the world and all of these other things. And sometimes when people say, "Is this an artificial intelligence?" they imagine an AGI. I think I said this in a previous session, but I try to avoid any sort of philosophical discussions about AI beyond the ethics of the work that we're doing. I'm not sure it's terribly helpful, and we're not AI theorists. We are users of AI, right? We apply AI rather than theorize about it. So I like to think of it as the difference between sort of like engineering and theology, like, whether you're making stuff or whether you're thinking about, the big questions in the world, and what we're really focused on is sort of making stuff. So without further ado, we're going to cover how machines learn. So the components of an ML system or an AI system are, first of all, data. So it's really important that the machine is able to observe the real world in some way. And the way that it observes the real world is by us feeding it data. And that could be an Excel spreadsheet. It could be as simple as, stuff that you find in a table in Excel, or it could be as complex as a feed of audio, which might go into your Alexa. It might be visual systems that go into driverless cars and other such things. But it's key that there is a flow of data that in some way represents the real world. Next is an algorithm. So typically, if you're going to work with a machine learning engineer, they're going to have a little a sort of dictionary of algorithms they can use that feel applicable to particular use cases. So in a minute, we're going to do some work with an algorithm called linear regression, which is really good at finding the relationship between two values in a way that could be expressed as a straight line. Next is training time. So this is where you take the algorithm and you apply it to the data, and you get it to understand the data and measure how right or wrong it is, and then keep on iterating until it's more right than it's wrong. And then the result of that is a model. So a model is a piece of code that is the combination of the algorithm and its learnings from its data. And that model can then be used to do what we wanted it to do in the first place, make a prediction, generate some art, do whatever it is that we originally planned for it to do. There's a really important distinction here in terms of algorithm versus model, in that a lot of algorithms are open and reusable. A lot of models aren't. So for example, GPT, the algorithm, the idea behind GPT is freely usable. But the specific model that they've trained and they've spent millions and millions of dollars training isn't free. And that's part of their commercial model. And that's something we'll discuss a little bit later. So this is the bit where I ask you to sort of get pen and paper out. So this is a chart of life satisfaction by income by country. So each of these dots is a country. Along the bottom is the sort of nominal GDP per capita, so how much the average earning is, and then going up the sort of left-hand side is life satisfaction on a scale out of 10. So you can see there's a general positive relationship between earnings and satisfaction at a country level. So those countries where people earn more tend to be happier than those countries where people earn a little bit less. So what I want you to do is on your notepad, and again, you don't have to show anyone your workings on this. It's just to help learn as you go. I'd like for you to plot a similar data set. You could either try and trace something very similar to this, or maybe you can draw something like I don't know, house price versus proximity to a city, or or anything else where there might be like a linear relationship between things, where a scatter might look a little bit like this. You don't even have to think up a data set. Even just having lots of dots on paper would be a helpful way of thinking this through. So looking at this data set, I think we can all pretty much see what a good line through this would be, right? If you were to get a ruler and sort of pop it onto your screen now, you could probably line it up with a lot of the dots to give some indication of the relationship between these values, between income and happiness. So what I'm going to do is I'm going to give a guess. I'm going to give this guess here. So maybe pop it in the chat. Does anyone think that's a good line for us to plot against? If so, why? If not, why? So if anyone wants to shout out on their mic as well, I'm perfectly happy to hear. There's a little hint here in the colour.
That's an awful line.
That's a bad line, isn't it? Who's this?
It's Charlie.
Hi, Charlie. Yeah, you're right. It's a really bad line, isn't it? And why is it a bad line?
It's far too low. It hasn't got proximity to most of the data.
Yes, you're absolutely spot on. It's really far away from all the different data points, isn't it? So we can measure how right or wrong we are by adding up the distance between any of these data points and the line. So you see here, there's one really far away in the top right. So we'd measure that and we'd add that to the next dot next to it. And that would give us some idea of how wrong we are. And Charlie's absolutely right. We're really, really wrong. So what we would do after that is we try again, right? So we're going to try again with this line. Charlie, you think this one's a little bit better?
It's much better. We've gone a little bit too high, but yeah, it's clearly better if you're measuring the average distance.
Perfect, perfect. And when you say high, you've unlocked one of the variables here. So the two variables that we're trying to calculate are the steepness of the line and its intersection. So is it something that comes in, around 7 or 7.5? And is it something that's very steep or very shallow like this initial red line? So we're going to try one more time. And this is our final example. This isn't mathematically correct, this one, by the way. I think the actual line is a little different to this, but I think this is a pretty good example now, because again, if we added up the distance between the lines, the green line and all of the data points, we would see that this is the lowest it could possibly be, and in fact it actually cuts right the way through some of the data points that you can see here on this screen. So hopefully you've been sort of drawing lines along, or at least maybe you drew a line right the way through the middle as soon as we were talking about this and you nailed it the first time round. But essentially that's what a basic machine learning system is doing. It's attempting to solve a problem, it's measuring how right or wrong it is, and then it's trying again with the goal of optimizing and minimizing that, what we call error. And that's exactly what we've done here. So if you take those other two lines away, this is our sort of, our best line so far. And then if you take the dots away, the thing that we have left with is a model, right? So can someone tell me, so based on this data set, GDP per person in the UK is around $40,000. Can someone tell me roughly what their life satisfaction is going to be based on this model? So maybe you can pop it in the chat or shout it out.
6.5?
Yes,
5.8.
that's perfect. Yeah, exactly. Between 6 and 6.5. That's exactly it. So this model now is a simplification and a generalization of that original data set that we can use to make predictions based on data that we've not seen before. So this isn't the same data set, but this is an example of linear regression actually working. So you can see the line is wobbling about and trying to find a place to settle, and eventually when it lands at the mathematical minimum error, you'll see that it settles, and then the resulting line is the model that we're sort of working with. And this is a hugely versatile. First of all, the idea of optimizing a problem is hugely versatile, and it's used in so many different so many different contexts. You know, even in the very most cutting edge generative models, they use this very same approach of optimizing against a problem. And then even this basic idea of just like trying to cut a straight line through stuff so you can explore the relationship between them is super, super useful. We had a toy model that we used in digital a while ago where we took everybody's estimates about websites that we're building and literally said, you know, based on the number of pages and complexity, what should the overall cost be? Now, it worked really well, but it was no substitute for, you know, proper estimation, but it was really good for doing something, you know, on the back of a napkin. Now, the good news is we could do way more than just plot straight lines through things, right? Because you could probably imagine that that's somewhat limiting. So first of all, I'd like to reassure everyone that you could do bendy lines if you want to, and that's a thing called polynomial regression, where we plot a bendy line through data sets. We can also do stuff that's not just numbers to numbers. So we could do like categorical stuff. So is something an A, B, or C? And we can also do like binary stuff. So is something yes or no? And you can have lots of different data sources as well. So in this example, we had, you know, one data source predicting one outcome. You can have multiple data sources. We call them features, and they can be of lots of different types. So we've talked about numbers. It could be categorical. It could be binary. It could be words if you're doing social listening. It could be images, sound, any sensor data. You know, anything that you might find useful to model against. And it was with this in mind that we did the Cavonia Cough Predictor project a couple of years ago. So you might have been on the previous session where we mentioned this, but the summary is we created a model that can predict coughs occurring across cities across the UK, and then if we thought coughs were occurring, then we would spend more on advertising in that area, and then if we thought coughs weren't occurring, then we would turn advertising off. We did weekly predictions, and the goal was to, in the words of the client, get ads under the nose of people with coughs. So this is one of those problems that like sounds like super direct and straightforward, and I think every client has a problem along these lines. Find people that need our products, show them our ads. So we thought, could we determine if a region has a particular cough outbreak, and therefore could we use this to optimize ad spend? So first of all, we decided on a yes/no output. So the thing we did just now with linear regression gives us a number output, but we actually went for yes/no instead. The reason we went for yes/no is because we wanted to turn advertising on or off, right? And having a number output, like, I don't know, percentage of the population with a cough, wouldn't have been that useful, because that would have required a lot more interpretation to decide whether we wanted to turn something on or off. So we used a binary fast forest algorithm, which is a simple and explainable algorithm that gives you some idea of what factors go into it. And we combined open and commercial data in order to do that. So there's data from the health services, there was data from, you know, weather and stuff like that. And we brought all of those together to try and understand what contributes to us being able to predict this. So we did 12 cities across the entire nation. Unfortunately, you know, we didn't cover Scotland particularly well because our data set didn't have data on that, and we wanted to correspond with TV buying areas, and the TV buying areas are quite sort of broad. In the lab, we got about 90% accuracy. So based on historic data, we can predict a cough outbreak to within 90% accuracy. And we found that feels like temperature was a real key feature. So meteorologically, there's a difference between the atmospheric temperature and then what it feels like. So they could be like wind chill, they could be moisture, they could be cloud cover, and these things all may make it feel sort of colder or hotter than it actually is. And we found that feels like temperature was a really key indicator for whether people actually went on to develop coughs. When it came to actually using it, we attempted to make 360 predictions, and 285 of them were correct. So that's an accuracy of around 79%. And only 51 of those predictions were false positives, where we would have had the client buying ads in areas where coughs weren't occurring. So we think the accuracy is around 79%, and we think the efficiency of this algorithm is around 86%. And you can see month by month our accuracy and our efficiency, was pretty high. The sort of worst month we had was February, and that's because we have a tendency to over predict the possibility of a cough outbreak. One interesting thing you might see here is that in March 2020, we predicted an unusual uptick in coughs. Turns out that was COVID. I'm not saying we predicted COVID, but it's just really weird timing that we happened to be running this campaign right as COVID started, because in a typical season, you wouldn't see a big increase in March like we do in this one. So what we found when we analysed the performance of the algorithm is that there was a big bias towards predicting outbreaks. So there were 160 or so outbreaks. We predicted 190 of them. And then when there were no outbreaks, we didn't predict as many of them as we should have. And this is a really great lesson in problem framing, which is a key part of some of the flaws that we see in AIs typically. Because at the start of the project, we asked ourselves, can we predict outbreaks? We didn't ask ourselves, can we spot opportunities to optimize? And if we had have said, can we spot opportunities to optimize, then our algorithm could have performed better. So this is a real insight into how algorithms can make mistakes and sometimes even do damage by asking the wrong question. So probably the most famous example of this is YouTube. YouTube is optimized with a single goal in mind, which is to have you spend as much time on YouTube as possible. And that means they serve you content that has you watching more. There's no judgment about that content, right? They don't understand what's left wing and what's right wing. They don't understand what's about gaming and what's about, I don't know, golf. All they understand is, according to users like you, this is content that keeps you watching for longer. And unfortunately, what we found as society is that the content that keeps people watching longer tends to err towards content that makes people react in extreme ways, that might repulse people or might engage people politically or might be controversial or might cause arguments or whatever else. So YouTube is a great case study in optimizing for the wrong thing. And the cough predictor, we believe, would have been better if we had optimized for opportunities to optimize rather than cough outbreaks. So what about generative AI? So I'm going to ask you to get your notepads back out again. And you're going to imagine that we've got a data set that looks a little bit like this. So the job of a generative AI is to produce new data that looks like the data that was given, right? So ChatGPT, for example, is a generative AI that talks, that writes words. And the job of ChatGPT is to write words that look like a lot of the words that it was trained on. With Midjourney and Stable Diffusion, the image generators, the job of those algorithms is to generate images that look like the ones that it was trained on, obviously constrained to the words that people put in. So what we're going to do for this model is we're going to draw a box instead. So hopefully you've got a little bit of a scatter on your notepad, and you're going to draw a box around it. Charlie, I hope you don't mind. I'm going to pick on you again because you were so good last time. Where would you draw the box around this to guarantee that any points that we pick within that box will look like the existing points on screen?
I have a bit of a relationship with that.
Okay, so it's harder because it's obviously more diffuse.
Well, we're saying
probably
one box, so a big old rectangle.
a big rectangle, so not just to contain the dots, but theoretically to be closest to the most dots, essentially.
Yeah, perhaps. Yeah, that's a great shout.
Yeah.
Go for it.
Okay, so I'd probably start. My top left point would be in that quadrant of 4 dots you got to the top left.
Perfect.
And I'd probably run it right across to roughly the middle of the kind of the right square, and I'd probably drop it down and stop it kind of in the middle of the bottom right square, and I'd go off to the left and finish that kind of middle of the bottom left square.
Perfect. That's great. That's a really, really great attempt. And I suppose the bit that you would miss if you did that is that if we constrain the points that our model generates to the box you've drawn, it won't ever be able to draw ones that are like the ones in the periphery. So what I would do is I would draw
Nice,
one
okay.
box capturing all of them. Yeah, I think you get it.
Yeah.
Cool, fantastic. So if we now pick a random point in this box, there's a pretty good chance it's going to resemble the other data points that are there, and therefore be a credible new generation. However, there's a hidden rule behind where all these dots are. If you're a geography nerd, you might have spotted that largely corresponds to the land masses and population centres on Earth. So with our box in mind, with our model in mind, it's still a pretty good estimation. But if you picked a random spot within this box, there's a pretty good chance you're going to get the Indian Ocean, the Atlantic Ocean, the Pacific. There may be a chance that you even miss areas that weren't in the original data set. So Alaska, for example, is missing from our original data set. And therefore you'd never be able to generate a data point that is a sort of population center in Alaska. So sorry again, Charlie, to pick on you, but how would you improve this model now? So let's say we're not constrained to just one box now. What would you do?
Yeah, you probably do more boxes to kind of to basically improve how closely the boxes match the underlying data source.
That's exactly it. So you might do a box around North America, a box around South America, a box around Africa. We might have a box for each continent, or even more granular than that. And then we can constrain our model to only pick dots on those boxes, right?
Yeah, that would make sense.
Cool, awesome. Thanks so much, mate. And sorry to pick on you. I think that's the last of the questions for now. So the key point here is that a model is a simplification. It's a generalization. Granted, it's a sophisticated one, and it's one that requires technical expertise. But the point is that it's never going to have the very same ability to predict and operate on the real world as the original underlying distribution. So if you look at the regression example, our straight line missed a lot of points, and actually even our best straight line was quite far away from some data points. And then with the generative model, our first box that Charlie and I drew was one that missed a lot of things. It missed Alaska, and you can actually, generate data points that exist in the middle of the ocean, which wouldn't make any sense at all. So we've got to remember that the model is a product of the data that we feed it, the algorithm that we pick. So is it one box? Is it many boxes? Is it a straight line? Is it a bendy line? And then giving it time to learn the data as well. So we call this training time. So there are lots of challenges to an AI project. First of all is just not having enough data. And we hear a lot of clients complain about this. We don't have the data to do X. We don't have the data to do Y. The good news is this is changing. So first of all, our clients are producing more data than ever before. There's lots of clients now that are using customer data platforms and analytics and other such things. Also, sometimes when clients say they don't have enough data, they often mean I don't have enough data in the right place or in the right format. And actually, there are new techniques that can help us create structured data out of unstructured data now, which is great for if people have lots of, I don't know, logs of emails or chats that they've had with their, customer services team or any unstructured data like that. Then there's non-representative data. So sometimes you have a lot of data, but it doesn't line up well with the problem at hand. There's not enough high quality data sometimes. So it might be that, you have lots of data, but it's not particularly well formed, or I don't know, it excludes areas of your business or, areas of the market in a way that might cause biases. There's irrelevant data. So when we were doing the cough predictor, we found that there are a lot of factors regards people's health, regards the weather that don't really do a good job of correlating to whether there's going to be a cough outbreak. And there are two phenomena as well called overfitting and underfitting, which are quite illuminating if you consider maybe the experience you've had with ChatGPT. So overfitting is when you create a model that too accurately describes the input data, and therefore it fails to generalize. So if you look at if we go back to our previous line, sorry to skip around, it might be that we create a bendy line that touches each and every one of these data points. But that would mean if we wanted to predict another data point, it would be really hard to do that, or at least do that accurately. And the bendy line might go off in directions that really doesn't make sense. So that's overfitting. And then underfitting is doing what we did at the start, which is just doing a really bad guess for the data. And therefore, what's predicted out of the model is junk. And the reason I say this is important for GPT, skipping back to my original slide. The reason I say this is important to GPT is because some people think GPT is boring. It's not really good at exploring creative ideas, and it doesn't think of anything original. It might be slightly overfitted. Other people think GPT talks crap. Some people think that GPT fibs and lies and makes stuff up, particularly if you ask it technical questions. Well, that would be underfitting. So there's a really big challenge in creating models, particularly generative models, that sufficiently balance the difficulties between overfitting and underfitting. So what's ML great for? So ML is great for problems where there are lots of rules that need to be written but aren't otherwise expressed. It's also really good for complex problems where no traditional methods already work. So in the self-driving car world, it's impossible to code a self-driving car by hand. You'd write millions and millions and millions of lines, and it would drive really badly. So it's great to think of stuff that we've tried before that was previously impractical or impossible. So anything along the lines of wouldn't it be great if could be a good opportunity to apply ML and AI. Fluctuating environments are great as well. So if you consider Cavonia, we had new health data and new weather data coming in regularly. Now we could have done the maths, right? We could have crunched the numbers and made a prediction for each of the 12 cities each day the weather changed. It would have been really difficult. It would have been really impractical, and it wouldn't have met the project goals of allowing us to, adapt our spend regularly. And then finally, ML's great for getting insight about lots of complex or poorly structured data. And the best example I could think of is CRM. If you want to throw AI against your CRM system, there's a pretty good chance it's going to be able to find audiences you didn't know existed. So there could be a tiny niche of, I don't know, dads that are really into cycling, that are repeat customers for a particular reason, that your brand planning or your typical sort of marketing hat would never identify, but doing data analysis using AI and ML could do. So moving on to how these things are made in the big tech world, it's worth acknowledging the difference between the amazing breakthroughs that are happening at places like Google and Microsoft and OpenAI and the work that we're doing. Because let's be honest, it's a completely different setup, right? They've got literally tens of thousands of people working on this at any given time. They've got literally billions of pounds being spent on this. So the three things that they've got in abundance are what I like to call petabytes, processing, and PhDs. So the first is petabytes. So petabytes of data, thousands and thousands and thousands of terabytes of data. There's this famous paper from Microsoft that basically says there's no point innovating when it comes to algorithms, because very different machine learning algorithms basically perform the same if you just throw shed loads of data at them, which is really interesting because that has shaped the way that the machine learning world has developed over the last 20 years. This idea that there is an unreasonable effectiveness of data. There's no point sweating the details of a particular algorithm when you can actually spend time gathering more data and getting roughly the same results. And that's led to this explosion of an idea called big data. There's all these hypotheses that data is the new oil, data is more valuable than anything else. And that's why big companies like Facebook and Google and YouTube and everything else obsessively collect data, even if they don't necessarily know how to use it immediately, because there's hidden value in that data. So the next thing is, moving on from that, cutting edge models are huge. So we've talked about petabytes of data. It's absurd how big some of these models are. So first of all, DALL-E, a relatively simple image generator, certainly simple compared to Midjourney today, was trained on 400 million combinations of images and descriptions of images. So I don't think there's a client on our books that has access to 400 million of anything for us to do analysis on. GPT-3, this isn't the most cutting edge version of GPT-3. The GPT-3's model has 175 billion parameters inside it. So our linear regression model had 2 parameters. Our generative model for geographic data points had like 4 parameters in it. GPT-3 has 175 billion parameters built into it. And then finally, GPT-4 was trained on 10 trillion words. So if you consider War and Peace is about 500,000 words, GPT-4 was trained on 10 trillion, an impossibly large amount of data. And that's how it understands, what word should come next when it has to generate new text. And then finally, processing. Sorry, not finally processing, we've got PhDs outside this, but onto processing. This is the NVIDIA A100. This is a chip that until recently was the leading AI chip. It's so powerful, it's subject to export bans because people are concerned about how the chip can be misused in an AI context. They also cost 10 grand a pop, which means that most people are unable to use one, let alone networks of them. And the performance of a single A100 chip is about 8 times higher than the performance of a PS5. And a typical server might have 8 of these chips in there. So a typical AI server would have 64 times the power of a PS5, which is crazy when you think of it, because that's a lot of compute, that's a lot of energy. And this is where a lot of the carbon inefficiencies of AI comes from. So when OpenAI trained GPT-4, they used 25,000 of these chips in an enormous network. And even with 25,000 of the most powerful chips all connected together, it still took 3 months solid of time to train GPT-4. So that's where we worked out that they burned more carbon than 1,000 flights from San Francisco to New York. Think of all the electricity running into all these chips, and then all these chips end up getting hot because they're being used, just like your laptop does on a hot day when you're plowing through your emails. So all of that heat requires cooling and disbursement. So it costs them millions and millions of dollars. I mean, the chips alone is tens of millions of dollars. The electricity cost is tens of millions of dollars. The interesting thing is we're able to invert some of this, right? So when we did the Praha generative AI project, it was roughly the time that Midjourney launched. And actually, it only took us about 2 weeks to train it. We trained on an A6000, and our training costs cost less than £2,000 to do that. So this is a really great example of if you've got a very specific problem to solve and the right know-how, you can do so at a tiny fraction of the cost and the complexity of these enormous sort of cutting edge AIs. And then finally, PhDs. So there's a lot of research going into AI. So even in 2021, so this is before Midjourney, this is before ChatGPT, there are thousands of publications being made of AI. So 49,000 AI publications from universities in 2021. And it's the same with code as well. So there are 348,000, or at least in 2022, there are 348,000 AI projects on the coding platform GitHub that are available for people to contribute to and engage with, which is a huge explosion. So there's a lot of research interest, there's a lot of coding interest, there's a lot of practical interest because people are starting to apply AI and machine learning to solve problems like predicting whether or not there'll be crop outbreaks. So how do we compete in this space? So first of all, we stand on the shoulders of giants. So we leverage open source code, open data, and open research for all of our projects. There's nothing we can do without relying in some way on work that other people have done. And this is the great joy of the AI world and the coding world generally, is that there is so much open collaboration that we can work off of and improve and specialize. Next is we're fast followers. So we're immersed in the topic and we regularly read about, give talks on, experiment with, and build new AIs around the cutting edge of research. So one great example is GPT-4 was announced on a Saturday. by Tuesday, we already had a specialized GPT-4 model being demonstrated to one of our clients to give some idea of how they could use generative AI to help with their new product development process. So just like a matter of even hours after it's announced, we're able to use it. We also tend to use a just enough process when it comes to, or approach when it comes to AI and machine learning. So we only use the data algorithms and training resources that are enough to solve our problem. So although the unreasonable effectiveness of data could help us, the point is that we don't want to waste resources, and we have techniques for using limited resources and achieving good outcomes. In particular, we don't apply new tech for the sake of it. And then finally, and most importantly, and this is the thing that I want you all to help me with, is domain expertise. We have a deep knowledge of our industry, of marketing and communications. We have a deep knowledge of our clients. We have a deep knowledge of their customers. And we use them to solve very discrete, very direct problems that are high impact for our clients. So there's no, we've just been told the client wants an AI. We don't really know what the problem is, but we have to prove to them we're using AI. That's completely against how we work with these clients, or how we try to solve problems. So finally, we like to focus on sustainability when building AIs because, again, this carbon cost is absurd. So we have a hierarchy in terms of how we like to approach problems, again, echoing our sort of approach earlier of just enough. So to start with, we would use prompt engineering. So rather than trying to build an algorithm of our own, we would integrate with an existing model and give it very specific instructions on how it might solve our problem. Next is one-shot and few-shot prompt engineering. So this is where we say, okay, I'm going to give you some examples of what's right, and you're going to try and follow my lead in terms of what's right. There's also retrieval augmented generation. So this is where we say, listen, I've half solved the problem for you. I found a data point that's very important to the answer of this problem, and I need you to make the final decision based on this data point. And this is something that I've been talking to the Mission Made team a lot about, because we think that this could power like a new generation of like search and chat-based experiences for websites. Then we do fine tuning. So it might be that if none of these processes work, we do a little bit of training on top of an existing model using fine tunings. And then finally, we might do transfer learning. So transfer learning is when you take an existing model produced by someone else and you just add a layer on top of it, you specialize on top of it. And that's how for PwC, we were able to get brilliant results in a matter of sort of days and weeks in terms of project time, and minutes in terms of training time, on top of a model that actually took many months and huge amounts of data to train. So we're able to specialize existing models to get incredible results. So GPT-4, for example, used 62 million kilowatt hours to train, whereas our Praha AI used just a few hundred kilowatt hours, which is something we're particularly proud of. It's, as I say, a low carbon solution to a very complex problem. So rounding things up again, my goals for this session was that I don't want to make you data scientists. Hopefully you feel a little bit closer now you've drawn some graphs and created some models by hand. I wanted to give you enough awareness and reassurance that we could do AI well. So hopefully, if a client approaches you and asks about our AI chops, hopefully now you know that this isn't something that we've just spun up overnight. It's something we've been doing for years, something that we've got award-winning expertise in, and something that we know deeply and can do well. Hopefully you know our offer a little bit better. I know I've not pitched this as a sales deck, and I can help you with a sales deck if a client is interested. But hopefully you realise that we solve problems using an incremental process, that we have a low carbon offer, and that we're really focused on getting the best results with the fewest resources. And then hopefully you've learned a couple of things about how models are made so you can avoid common mistakes. So knowing, for example, poor quality data would be a problem. Knowing, for example, a model is derived entirely by the data that is given can help you frame a problem and I suppose pre-qualify, issues that we might run into when it comes to it. So that's the whole thing. We ran through it quite quickly. I appreciate it's a dizzying pace. There's quite a lot to sort of learn quickly. Have we got a question in the chat? Are there any starting points for learning more about this as a complete novice? Yes, there are. I've got some great book recommendations if you're a book person. I've got some great course recommendations as well. I suppose the question would be, to what end? Do you want to become a coder, right? Do you want to join the team and help us code AIs, or do you want to sell AIs better to your clients? So, Catherine, really interested to hear that. Would love to chat about training resources separately. Eleni, I think Russ also has a LinkedIn sort of training program thing in the works, doesn't he?
Yes, we have that, and I can post that into the chat for everyone to see as well. I have identified in the previous session as well some hot topics for AI and what's mostly, visited and the 10 most popular sessions within LinkedIn Learning. So I'll post that into that chat as well for everyone to see in their free time and, engage with AI. I think it's a fantastic topic and it's an emerging topic. So we all should, in a sense, learn more.
Yeah.
So I'll post those things on the chat.
Cool. No, that sounds great. And as I said in the last chat, if something doesn't come to you now, or you don't feel like you can ask the question in front of 57 other people, then please message me. I'm happy to talk about any of this. In particular, I think I said before, any questions on the lines of "wouldn't it be great if," or "my client would love," or "it would be brilliant if," or anything along those lines, where a conventional approach might not have been sufficient. So there you go. Fantastic. Well, great to see you all, and thanks for listening. I really appreciate all of you people that sort of on what resources in terms of implementing machine capabilities on demand. Okay, cool. So on demand, there's quite a lot around automated machine learning, where you can take a data set and get an indicative view of what the performance might be without a huge amount of effort or fuss. So Microsoft have a package for that in Azure, which is worth looking at. I'm not sure if that's answered your question. Happily chat offline though, if you want to, Matthew. Brilliant. Well, we should let you guys go then.
Really interesting stuff. If you've got any more questions, yes, indeed, pop them into the chat. We will sit and still answer those after the session finishes as well. You'll have a recording on the Launchpad by tomorrow from both of the sessions, the morning one and the afternoon one. So yeah, that's me as well saying thank you to everyone and have a lovely, lovely afternoon.